Imagine tossing a pebble into a still pond. What happens? Ripples, right? These ripples carry energy outward, making the water bob up and down as they pass. Now imagine something similar happening to the fabric of the universe itself. Massive objects like black holes or neutron stars colliding create disturbances in spacetime. These disturbances are what we call gravitational waves. Gravitational waves are ripples in spacetime, traveling at the speed of light. They carry information about cosmic events, opening a new way to observe the universe. To grasp gravitational waves, visualize spacetime as a flexible sheet. Imagine a trampoline as a model. A bowling ball creates a dip, representing gravity. A marble's path curves, influenced by the dip. This is how gravity works in our universe. Moving objects create ripples, like gravitational waves. These waves travel, carrying cosmic information. The study of gravitational waves is not merely about confirming Einstein's theories, it's about gaining a deeper understanding of the universe we inhabit. These waves carry information about some of the most extreme environments in the cosmos, places where gravity is at its most powerful, black holes, neutron stars, and the very moments after the Big Bang. By studying these waves, we can glean insights into the nature of gravity itself, testing our current understanding and potentially uncovering new physics. Imagine being able to witness the collision of two black holes, an event so cataclysmic that it sends ripples through the very fabric of spacetime. Gravitational waves allow us to do just that. They provide a front-row seat to some of the most energetic events in the universe, events that were previously shrouded in darkness. Before the detection of gravitational waves, our understanding of these events was largely theoretical, based on observations of electromagnetic radiation like light and radio waves. However, gravitational waves provide a completely independent source of information, allowing us to confirm our theories and refine our models. Moreover, gravitational waves can penetrate regions of space that are opaque to light. For example, the very early universe, just moments after the Big Bang, was so dense that light couldn't escape. Gravitational waves, however, could have traveled unimpeded through this dense primordial soup, carrying with them information about the universe's earliest moments. Detecting gravitational waves is no easy feat. Remember those minuscule ripples, smaller than the width of an atom? Imagine trying to hear a whisper in a hurricane. That's the challenge scientists faced when trying to detect these elusive waves. It required not only a deep understanding of Einstein's theories, but also the development of some of the most sensitive scientific instruments ever built. The quest to detect gravitational waves began decades ago, driven by the desire to test Einstein's predictions and open a new window into the universe. Early attempts involved using massive aluminum cylinders, hoping to detect the vibrations induced by passing gravitational waves. These efforts, while pioneering, were ultimately unsuccessful. The technology simply wasn't sensitive enough to pick up the faint whispers of these cosmic disturbances. It wasn't until the late 20th century that technology caught up with scientific ambition. A new generation of detectors, based on a technique called laser interferometry, emerged as the most promising approach. These detectors, with their unparalleled sensitivity, would finally usher in the era of gravitational wave astronomy. One such detector, the Laser Interferometer Gravitational Wave Observatory, LIGO, would go on to make history. Imagine a giant L-shaped ruler, its arms stretching for miles, meticulously engineered to detect the tiniest of changes in length. That's LIGO in a nutshell. Located in two sites across the United States, one in Hanford, Washington, and the other in Livingston, Louisiana. LIGO stands as a testament to human ingenuity and our relentless pursuit of scientific discovery. Each arm of the LIGO detector is a marvel of engineering, a 4-kilometer-long vacuum tube housing a powerful laser system. These lasers are not your everyday laser pointers. They are incredibly stable and precise, capable of measuring distances with astonishing accuracy. The basic principle behind LIGO is surprisingly simple, even if its execution is anything but. A single laser beam is split into two, with each beam traveling down one of the detector's arms. At the end of each arm, a mirror reflects the beam back to its starting point. If a gravitational wave passes through the detector, it will ever so slightly stretch and squeeze spacetime, causing a minuscule change in the length of the arms. This change in length, in turn, affects the time it takes for the laser beams to travel back and forth. By carefully measuring the difference in arrival time between the two beams, scientists can detect the passage of a gravitational wave. The sensitivity of LIGO is mind-boggling. It can detect changes in length thousands of times smaller than the nucleus of an atom. To achieve this level of precision, every aspect of the detector has to be meticulously engineered and isolated from external disturbances. The mirrors, for instance, are suspended from sophisticated isolation systems that dampen any vibrations from the outside world, from passing trucks to seismic waves. Even the air inside the vacuum tubes is carefully controlled to minimize any fluctuations in density that could affect the laser beams. The lasers themselves are marvels of modern technology. They are stabilized to ensure that their frequency and power remain constant over time. Any fluctuations in the laser light could drown out the subtle signals from gravitational waves. LIGO is essentially a giant, incredibly sensitive microphone, tuned to listen for the faint whispers of gravitational waves rippling through space-time. When a gravitational wave passes through the detector, it creates a characteristic chirp signal in the data, a telltale sign of a cosmic collision. This chirp represents the stretching and squeezing of space-time as the wave passes through, like the ringing of a bell after it's been struck. The first detection of a gravitational wave, announced in 2016, sent shockwaves through the scientific community. It was a historic achievement, confirming a century-old prediction by Einstein and ushering in a new era of gravitational wave astronomy. LIGO doesn't stand alone in its quest to listen to the cosmos. Other gravitational wave detectors around the world, like Virgo in Italy and Kagra in Japan, have joined the hunt, forming a global network of listening stations. Having multiple detectors is crucial for several reasons. First, it allows scientists to triangulate the source of a gravitational wave, much like GPS satellites pinpoint a location on Earth. By comparing the arrival times of a signal at different detectors, scientists can determine the direction from which the wave originated. Second, a global network helps to rule out false signals. Earth is a noisy place, and even with all the sophisticated isolation systems, LIGO and other detectors can pick up vibrations from earthquakes, traffic, and even ocean waves crashing on distant shores. By requiring a signal to appear at multiple detectors separated by thousands of miles, scientists can be more confident that they are indeed seeing a gravitational wave and not just local interference. The future of gravitational wave astronomy is bright. New detectors are being planned and existing ones are being upgraded, promising even greater sensitivity and the ability to detect a wider range of cosmic events. As the field matures, we can expect to unravel more secrets of the universe, from the collisions of black holes to the echoes of the Big Bang itself. Cosmic archaeology, unraveling the universe's hidden history. Imagine piecing together Earth's history by studying fossils. You'd have gaps, missing pieces lost to time. Gravitational waves offer a new way to study the universe's history. They carry echoes of events from billions of years ago. Traditional astronomy is like a photograph. Gravitational waves are like recordings. They let us peer into the distant past. Each detection brings us closer to understanding our place in the cosmos. Black hole mysteries, probing the hearts of darkness. Black holes, whose gravitational pull is so strong that not even light can escape, captivate scientists and the public alike. Gravitational wave astronomy has firmly established their existence. Before this, our understanding was indirect, based on their effects on surrounding matter. Observing star orbits and X-rays from gas spiraling into black holes provided clues. Gravitational waves offer a direct probe into these cosmic monsters. Colliding black holes release immense energy as gravitational waves. These signals reveal information about black holes' masses, spins, and spacetime properties. They also test Einstein's theory of general relativity. Gravitational wave astronomy has revealed surprises about black holes. It shows they come in a wider range of masses than previously thought. This raises new questions about their formation and role in galaxy evolution. Neutron star symphonies. Listening to the densest objects in the universe, neutron stars, formed from collapsed massive stars, pack the mass of our Sun into a city-sized sphere. A teaspoonful of neutron star material weighs billions of tons. Neutron stars are like giant atomic nuclei, with immense gravitational forces. They have magnetic fields trillions of times stronger than Earth's. Neutron star collisions produce powerful gravitational waves and cosmic fireworks. These events help scientists study matter under extreme conditions. Section 4. Beyond Einstein, Gravitational Waves as Probes of New Physics. Einstein's theory of general relativity has passed every test, but it can't be the final word on gravity. It's incompatible with quantum mechanics, suggesting a deeper theory unifying both. Gravitational waves offer clues about this new physics. They travel unimpeded, carrying pristine information about the universe. Ideal probes of the early universe, they could reveal deviations from general relativity. Some theories predict multiple polarizations of gravity, unlike the two in general relativity. Detecting these would be a smoking gun for new physics. Gravitational waves could also reveal exotic objects like cosmic strings or extra dimensions. Each discovery would revolutionize our understanding of the universe. The quest for new physics continues, with gravitational waves as our guide. The future promises groundbreaking revelations. Section 1. A new window into the cosmos. Groundbreaking discoveries with gravitational waves. Detecting gravitational waves is like gaining a new sense. These detectors reveal phenomena hidden from view. Gravitational wave astronomy has transformed our understanding of black holes and neutron stars. Each detection adds a piece to the cosmic puzzle. These discoveries have profound implications for our understanding of the universe. As detectors become more sensitive, we can expect an avalanche of new discoveries. The era of gravitational wave astronomy has just begun. The future promises awe-inspiring revelations. We are uncovering secrets that will reshape our understanding of the universe. Section 2. The First Whispers. Merging black holes and a new era of astronomy. The first detection of gravitational waves in 2016 was a watershed moment. It marked the beginning of gravitational wave astronomy. The signal was from two black holes spiraling towards each other. Their gravitational pull sent ripples through space-time. This detection confirmed black hole binaries and Einstein's theory. It opened a new way of studying the universe. Astronomers could now hear the cosmos. Since then, dozens of black hole mergers have been detected. We now know black hole binaries are common. Each detection adds to our understanding of these objects. We are piecing together their formation and evolution. Gravitational wave astronomy is revolutionizing our view of the universe. Section 3. Cosmic alchemy, neutron star collisions and the origin of heavy elements. The observation of a neutron star collision in 2017 showcased the power of gravitational wave astronomy. This event, GW170817, marked the era of multi-messenger astronomy. Neutron star collisions generate gravitational waves and vast amounts of matter. GW170817 was observed in both gravitational waves and light. The gravitational wave signal revealed the masses of the neutron stars. The light provided clues about the ejected material. Neutron star mergers are the cosmic factories of heavy elements like gold and platinum. This discovery solved a long-standing puzzle in astrophysics. The gold in your ring was forged in neutron star collisions. These events are now revealed through gravitational wave astronomy. We are uncovering the interconnectedness of the cosmos. Gravitational wave astronomy is transforming our understanding of the universe. Section 4. Echoes from the deep future quests in gravitational wave astronomy. The detection of gravitational waves has opened a new frontier in astronomy. As detectors become more sensitive, we can expect new discoveries. Detecting primordial gravitational waves would be a major breakthrough. These waves could provide a glimpse of the early universe. Another exciting avenue is the search for exotic objects like cosmic strings. These objects would have unique gravitational wave signatures. Gravitational waves provide a new way of seeing the universe. We are no longer limited to observing with light. As we explore this new frontier, we will make groundbreaking discoveries. We are unraveling the mysteries of the universe. The future of gravitational wave astronomy is filled with promise. Section 1. The challenge of silence. Filtering out the cosmic noise. Detecting gravitational waves is like having a conversation at a rock concert. The universe is noisy, filled with signals from various sources. Scientists have developed methods to filter out the noise. Detectors are built in isolated locations to reduce human-made noise. LIGO's detectors are in remote areas with low seismic activity. Sophisticated algorithms sift through data to identify gravitational wave signals. These algorithms act like noise-canceling headphones. They filter out unwanted signals. Scientists focus on the faint whispers of gravitational waves. Overcoming noise is a major challenge. The quest for clarity continues. Pushing the limits. Enhancing sensitivity for fainter whispers. Detecting faint gravitational waves requires unparalleled sensitivity. Instruments must measure disturbances smaller than a proton. Scientists are constantly improving detector design and reducing noise. One focus is improving the stability and power of lasers. New laser technologies could significantly reduce noise. Another focus is the design of mirrors in interferometers. New mirror coatings and suspension systems minimize vibrations. These advancements enhance detector sensitivity. We can probe deeper into the universe. Detecting fainter signals from distant events is the goal. The quest for greater sensitivity continues. Beyond the horizon. New instruments for a new era of discovery. Current ground-based detectors are just the first step. New instruments will expand our ability to detect gravitational waves. The Laser Interferometer Space Antenna, LISA, is a space-based observatory. LISA will detect lower-frequency gravitational waves. It will be sensitive to supermassive black hole mergers. These events provide insights into galaxy formation. New ground-based detectors like the Einstein telescope are also being developed. The Einstein telescope will be built underground to reduce noise. It will detect gravitational waves from distant sources. The future of gravitational wave astronomy is bright. A symphony of data, unraveling the universe's secrets through collaboration. Gravitational wave study is a global endeavor. Collaboration and data sharing are essential. The LIGO and Virgo collaborations involve scientists worldwide. These collaborations maximize scientific return. Sharing data and expertise enhances detection and analysis. The global network of detectors is expanding. Combining data from multiple detectors improves accuracy. Gravitational wave astronomy is in its infancy. Collaboration will lead to new discoveries and insights. Reflecting on the gravitational wave revolution. The detection of gravitational waves marks a profound shift in our cosmic perspective. Gravitational waves have given us a new way of perceiving the universe. We can now hear the whispers of black holes colliding, the death throes of massive stars, and perhaps even the faint echoes of the Big Bang. This newfound ability has revolutionized astronomy. Section 2. Unveiling the Invisible. The profound impact of gravitational wave astronomy. Gravitational wave astronomy has revolutionized our understanding of the universe. We now observe black hole mergers and neutron star collisions directly. These events reveal the formation of heavy elements and cosmic evolution. Future detectors promise even more groundbreaking discoveries. Section 3. The universe in a new light, expanding our cosmic perspective. The detection of gravitational waves has broadened our cosmic perspective. It has forced us to confront the limitations of our previous understanding of the universe. For centuries, our view of the cosmos has been shaped by light. These forms of electromagnetic radiation represent only a small fraction of the information out there. Gravitational waves travel virtually unimpeded, carrying pristine information. This makes them ideal probes of the early universe. By studying gravitational waves, we could unlock secrets about the Big Bang, the formation of the first stars and galaxies, and the nature of dark matter and dark energy. Gravitational waves could reveal exotic objects and phenomena. Each discovery would revolutionize our understanding of the universe, forcing us to re-evaluate our fundamental assumptions about reality. Section 4. Embracing the Unknown, a future filled with cosmic wonder. The era of gravitational wave astronomy has just begun, promising awe-inspiring revelations. As we explore this frontier, we will unravel the mysteries of the universe. The quest to study gravitational waves showcases human curiosity and collaboration. It is a global endeavor, uniting scientists to push knowledge boundaries. We stand on the cusp of a new era, reminded of the universe's vastness. Each discovery reshapes our understanding of the cosmos. The future of gravitational wave astronomy is bright, promising new discoveries. As we listen to the cosmic symphony, we embrace the unknown. The journey of discovery has just begun, inspiring future generations.